Okay, so this is the big video, well, a mini big video. Promise to give you QR decomposition, so here's the video. So the basics of QR decomposition is if you have a matrix A, so A1, A2, A3, it has to be a square matrix, but if you have a square matrix A, then you can decompose it into Q times R. And Q, as we saw previously with the Gram-Schmidt process, Q is the matrix we get from using the Gram-Schmidt process, or the orthogonal matrix. To be more specific, it is actually the orthonormal matrix. We just want to make sure that the norm of the vectors equals 1, so it's a unit vector. But Q in this case is the orthonormal matrix we get from the Gram-Schmidt process, and R is actually a upper triangular matrix. So you would only have, it's basically like the name says, right? You would only have this triangle. All the bottom triangle, the bottom left triangle would be filled with zeros, and the only part that actually has numbers, right, actual values, would be this top right triangle. So that's why it's called upper triangular matrix. And we'll go through kind of like the step by step, like the intuition of why the QR decomposition works, and why we need to know it. Like, what's the use for it? So first, if we talk about orthonormal vectors, right? The fun thing about orthonormal vectors, there's multiple ways to interpret how they look like, but one kind of a neat way to look at orthonormal vectors is it's just a unit rotation of the base of the regular normal, or quote unquote normal basis vector, right? So when we think of like regular coordinates, right, it's 0, or 1, 0 and 0, 1, right? So there's an x component and a y component, right? I component, j component, right? So that's like the quote unquote standard basis vector, right? And then orthonormal vectors, right? All orthonormal vectors are just rotations of the standard basis vector, right? So we have the standard basis vector here, right? E1, E2. You could put the names, the labels. So the red one could be E1, the blue one could be E2. But every single orthonormal vector you can get on a 2D graph, right? It's just a rotation, right? This is an orthonormal basis. This is an orthonormal, right? All these rotations, right? These are all the, those are the only possible orthonormal vectors you can get, right? So with that kind of like intuition in mind, keeping that in mind, I want to go through numerical stability. So we're taking a bit of a different, we're taking a bit of a tangent here, tangent, but this will come into play later on. So this graph is kind of just showing like the basic concept of numerical stability. All it is there's a more formal definition of numerical stability, depending on if you're working in linear, nonlinear, stuff like that. But the simple definition is that when you iterate a process, right? So when you put in, when you have errors in your input, those errors shouldn't become bigger in the output, right? And vice versa, right? If you have errors in the output, the errors in the input shouldn't get bigger, right? So that's forward propagation and back propagation, that's called, but all it is, right, it's like this diagram. So if we start, right, let's say hypothetically, right, if we start our journey, let's say at this point on the top here, right, this top corner point, so if we start our journey on this top corner point, right over here, oh, give me 1 second, right over here, there we go. If we start our journey at the top corner point, or not really corner, but top point, if we kind of follow the arrows, right, over time, no matter what error you have, right, so we started with a big error, right, quote unquote error initially, right, as we move forward in time, right, the error gets smaller and smaller and smaller and smaller and smaller, right, until it hits the middle point, right. It's called a fixed point in numerical analysis. In this case, we would call it stable, right? It's a stable fixed point. But all that is saying, right? If we're given some sort of input, right? Input or some sort of initial condition, right? Initial conditions. And if we have some sort of like noise or error in the beginning, then we'll still end up with this fixed point, right? We'll still end up with this fixed point in the end, right? So it's like a whirlpool, right? All the points, all the lines go towards that center point, right? It's like a whirlpool or it's like a drain, right? Now that's sometimes what it's called in differential equations, right? But you have this fixed point here, a whirlpool point. And so, right, now we went through orthonormal vectors, right, and numerical stability, right? So now we have to actually, we can tackle the question, why is why do we want to use QR decomposition? It's actually because QR decomposition is numerically stable. So if we take, I actually have to credit someone on Quora. I'll put that in the description below. I used a lot of his ideas, and I'll also put a lot of other references as well. But in this case, we've got, so if we have some sort of hypothetical system, right? So y is a vector, x is a vector, a is the matrix, right? As we mentioned earlier, and e is just the error in this case, right? So e stands for error, and what we can actually do, we know with QR decomposition, we can substitute a equals QR, right? We know that we can do that for square matrices that have that are invertible, right? That are invertible. So with that, now, right, we have y is equal to QR, x plus e, and then if we multiply both sides by the transpose of q, right? So we get this whole line. I'm not going to mention the whole thing, but we get this whole equation, and then because we know by definition, right, since we define q to be orthonormal, right, the transpose of an orthonormal vector times the orthonormal vector itself, right, qt times q is going to be equal to I, right, the identity matrix. And that makes sense, right? And that's because if you have orthonormal vectors, right, if you have orthonormal vectors, right, and if you transpose it, right, so if you flip it along its diagonal, since we know that the norms of the vectors, right, the norms of the vectors, they all have to equal 1, we're essentially just multiplying each vector by its own component, right? I'm kind of skipping a couple of steps here, but essentially, we're going to end up with the identity matrix. And so once we do that, we end up with this equation on the bottom, right? So we end up with this this equation on the bottom, right? Qty equals Rx plus Qte. And now we have, we were able to solve for y and Rx, right? The only thing really we're worried about is this error, right? The error is going to be what determines whether it's numerically stable or unstable. And in this case, we know that since Qt, right, Q transpose is also an orthogonal matrix, right? If we transpose an orthogonal matrix, orthonormal matrix, we're also going to get an orthonormal matrix. It'll be a bit, well, it'll be on its side, but we're still going to get it. So that means that the covariance of the error won't change. Basically, what that's saying is, graphically, right, what's happening when you multiply by the orthonormal matrix is you're multiplying each component separately, right? So you're multiplying all the x components separately, all the y components separately, and if it was 3-dimensional, right, all the z, right, and then so on and so forth. Because we're multiplying each component separately, right, the x coordinates won't affect the y coordinates, right, and the y coordinates won't affect the x coordinates, right, because they're orthonormal, right, they're 90 degrees to each other, right? They can't, right, because it's a orthonormal matrix. So because of that, right, the error can't change, right? The error can't, the error can change. Let me make it clear. The covariance of the error can't change, right? And to demonstrate that, I actually made a little bit of a script here. So all this is doing is it's creating or generating a bunch of scatterplot points, and we're going to also take the transpose, right? Transpose of the scatterplot point, and we're also going to take the orthonormal matrix multiplied by each point of the scatterplot, right? So what we'll end up with, so this top chart, the top chart is showing us the orthonormal, it's showing us the error, right? I'm just generating lots of random samples based on a Gaussian distribution, right? But it could be any sort of distribution, right? It just has to be random error, right? So the top part is random error, and this middle section is showing us the transpose, right? So it's flipping along the diagonal, and then what this bottom part is showing is actually the orthonormal matrix multiplied by the error points, right? The randomly generated error points. And so, and for the orthonormal matrix, it's also randomly generated as well, just to spice it up a little bit. But if we run this a couple of times, as you can see, give me a sec. Pretty much the covariance, right? The correlation, right? The correlation of x compared to y, it's not changing at all. And in fact, for those of you who are more perceptive, you might actually see that the transposed version, right? The transposed version of the randomly generated errors, right? The randomly generated error samples, that actually the transposed version is like a rotated version of the orthonormal matrix times the error samples, right? I'll post this code in the description below too, so you can kind of mess around with it. And so, that was just to show us, kind of just as like a numerical, almost, not really science, it's not really a science experiment, but a computer experiment, as you will, or numerical stability experiment. And it just showed us that the x and the y coordinates, right, they didn't correlate. There's no change in correlation, right, between the two. So just to make it more clear, right, this term covariance, all it's saying, there's a more technical and much more technical definition of it, but all it's saying is if one variable changes, the other variable changes, right? So if you have a graph like this, right, there's a tendency, right? If x is increasing, y is increasing, right? If you have a graph like this, if x is decreasing, y is decreasing, right? But if you have a graph like this, there's no correlation whatsoever, right? So 1, 2, 3. If you have these three graphs, each of them have different correlation, right? Different correlation. And what we're saying when the covariance doesn't change, right, is if the error, right, if the error has a positive correlation, right, so this is a positive correlation, then this QTE, right, Q transpose times E is also going to be positive, right? If error, I'll write over it. Don't worry, I'll erase it later on. If error, right, if error is positive, then QTE, right, QTE is also positive. QTE, might be hard to see, is also positive. Basically, the signs won't change, right? The correlation won't change. No, whether it's positive, negative, or zero, right, close to zero, it won't change the correlation, right? And that's just because the orthonormal matrix, right? The x can't affect the y's, and the y's can't affect the x, right? Because it's orthonormal. So now at the very end, to give you kind of like a taste of what's actually happening, right? For a visual, we've got vectors for matrix A, right? So we've got vectors for matrix A, right? So this is the vector that we want to QR decompose, right? So first, we want to come up with this. I'll give it a sec. We want to come up with an orthonormal vector Q for A, right? So as we mentioned earlier with the rotation, right? All orthonormal vectors are just rotations, right, of the standard basis vector. It's just a rotation. So in 3D, it's going to be a bit tricky, right? But it's exactly the same, right? All orthonormal vectors are just rotations of a standard basis vector. So what we're actually doing here is if we take this orthonormal vector, right? So we have the standard orthonormal vector, and if we just rotate it, right? Rotate it ever so slightly, boom, right? Now it's in 3D. It's in 3D, so it's not. It's a bit hard to see, but we want to align one of the vectors, right? One of the vectors for Q, the orthonormal vector, with one of the vectors for A, right? Matrix A, right? And what we're essentially doing here is we first want to align the vectors, right? So the first part, we want to align the vectors. Then secondly, we want to align a plane, right? We want to align a plane. So this schematic is kind of showing us what's actually happening, right? So since A is equal to Q times R, we've got this vector, right? We have a matching vector. We have this matching vector, but we also, then we want to have this matching plane, right? We want to have this matching plane. So a matching vector, a matching plane, and then finally, we want a matching volume. So that's what the upper triangular matrix is representing graphically, right? First, we have vectors in the same direction, right? Multiplied by a scalar, right? Multiplied by a scalar. So we will first want to match the orthonormal vector, right? So when we're rotating the orthonormal vector, just to go over it again, when we're rotating the orthonormal vector, we want to match first a vector, right? We want to match this vector direction, right? We want to match the direction of the vector. And then we're going to multiply by a scalar, right? With the upper triangular matrix. Secondly, right, then we want to match this plane, right? We want to match this plane. So that'll be a bit more tricky to manage, but it'll be a bit tricky to show in 3D. But we want to match this plane, right? So we're rotating across the plane. And third, we want to match this volume, right? So at the very end, I always say matching, right? But we're just leaving the vector as it is, right? Because we can't rotate it anymore. So a neat thing about this, we can actually just do 2 rotations, right? 2 rotations on whatever axes you'd like, right? They just have to be different axes, right? Rotation on the, let's say, x-axis, right, and the y-axis. You just need 2 rotations. And once you match the orthonormal vector to, so orthonormal vector Q to the vectors Q to the vectors for matrix A, then you're going to end up with, this, the matrix for R, right, which is represented by a vector, a plane, and a cube, or a volume. Vector, plane, and a volume. Of course, it's written in vector form, right? The matrix R is written in vector form, but graphically, right? Graphically, you can also look at it as there's a vector, there's a plane, and there's a volume. Right? Graphically, that would be equivalent. So now, after all this, you finally know how to do QR decomposition. Not only know how, but you understand why. Hopefully, you understand why QR decomposition is useful, because it's numerically stable. I hope you enjoyed. This took quite a long time to make. I was planning on adding a little bit more animation, but the Python file should be pretty fun for anyone who's looking to kind of experiment with it. And if you have any other questions, please let me know in the comments below. And if I made a mistake somewhere, also please let me know as well. I'd love to improve. Otherwise, I hope you have a wonderful day.